Hi, I'm Tim, and this is video number 11 in the series about anti-gravity matter. This video deals with the behaviour of the AGM exclusion density at large scale. This video series gives an overview. If you want more explanation, see the earlier videos or the documents linked to the website. This is an image from video number 3. The message from that video was that Bok globules just fill their AGM boundaries, and at the scale of this graph, the radius of the AGM boundary is proportional to the normal matter mass within the boundary. That's why smaller Bok globules are more dense. And so the radius of the AGM boundary is inversely proportional to the square root of the AGM exclusion density. Throughout this video, we're assuming that the AGM boundary is spherical. But what happens at larger scale? Let's zoom out. There are the same Bok globules at bottom right, sitting on their AGM exclusion density dotted line. It turns out that as the mass of the central normal matter object increases, the radius of the AGM boundary increases, and the AGM exclusion density looks like this. There are two separate behaviours here. At small scale, the radius of the AGM boundary is driven by AGM pressure. Anti-gravity between anti-gravity matter particles has little effect. At small scale, the graph has a slope of -0.5. But at large scale, the radius of the AGM boundary is driven by anti-gravity between anti-gravity matter particles. AGM pressure has little effect. The large-scale AGM exclusion density is independent of the mass inside the AGM boundary. These two behaviours are called anti-gravity dominated and AGM pressure dominated. So what about globular clusters? The Milky Way's globular clusters were covered in video number 8, and we need to just confirm that the explanation given in that video is still valid. So here's a quick refresher. Globular clusters are like this. Around the outside, the stars are below the AGM exclusion density. That means there's anti-gravity matter, shown in grey, in the space between the stars, and the stars are affected by AGM drag. But the stars in the centre have reached their AGM exclusion density. A shared AGM boundary has formed around the central region. There's no anti-gravity matter inside that shared AGM boundary, so the stars there aren't affected by drag and they retain their energy. A globular cluster that is unusually energetic will have a low density. It'll have many stars outside the smaller central shared AGM boundary. Those stars lose energy to AGM drag and the cluster gets denser. As the cluster gets denser, the rate of energy loss decreases. For this video, we're simply going to assume that the globular clusters end up with a mathematically similar density profile. So for example, the radius of the shared central AGM boundary is a constant fraction of the half-mass radius. When a globular cluster is in an anti-gravity matter wind, the ram pressure of the wind drives the AGM boundary inwards at the leading face, which makes the cluster denser. As explained in video number 8, the globular clusters that are lower down in the group on the graph are closer to the plane of the Milky Way. That means they aren't affected much by anti-gravity matter wind. But the radius that we measure for each cluster is much greater than the radius of the shared AGM boundary of the core. That means that on this graph, those globular clusters are moved along a vector that's something like that. To understand this vector, imagine starting with the core inside its shared AGM boundary on the AGM exclusion density line, then add a bit more mass and a lot more radius to get to the density and radius of the whole globular cluster. Just to be clear, the length and location of that vector is just an estimate to explain the concept. We don't know exactly where the AGM boundary is. The globular clusters that are higher up in the group are well away from the galaxy plane and are affected by a strong anti-gravity matter wind. One way of looking at this is that for them, the wind increases the effective AGM pressure and the whole lower sloping dotted line is moved upwards to round about here. Then the same vector can be used to connect each cluster to its core on the raised AGM exclusion density line. So you can see that the globular clusters are actually AGM pressure dominated, even though most of them are bigger than the limit between the two regions. The explanation in video number 8 stands. What about elliptical galaxies? Well, elliptical galaxies are structurally very similar to globular clusters. They're just much bigger. We'd expect their cores to be on the upper part of the AGM exclusion density line, well into the anti-gravity dominated region, and we'd expect the same vector to link their cores to their overall radius and density, like that. And indeed, it is possible to make a few assumptions and corral the elliptical galaxies into a region on the graph like that. The spread of galaxies left and right of the group may be caused by galaxies with high local velocity, which means we calculate an incorrect distance, and also galaxies with a high local velocity being made denser in the same way as some globular clusters, though in that case they'll have to be going very fast because they're well into the anti-gravity dominated region. So that's approximately the shape of the small and large scale AGM exclusion density line. The densities of Bok globules, globular clusters and elliptical galaxies are all heavily influenced by the anti-gravity matter atmosphere. And I'll finish the video by returning to the terminology list, and we've added the terms AGM pressure dominated and anti-gravity dominated, two behaviours of the AGM exclusion density as normal matter mass varies.